Okay, this first one up here, what is it that we're trying to figure out? So I need heat, so what unit am I looking for? I'm looking for calories. So I need something in here that's got calories. There's the only calorie thing. So I'm going to start off with 0.22 calories per gram degree C in the numerator. I need to get rid of the grams and the degree C that came along with that. So I'll throw 75 grams up here. That way the grams cancels out. I'm given two temperature values in degrees C. So what am I supposed to do with those? This is about, this thing was at 3 degrees Celsius and went up to 100 degrees Celsius. So it didn't gain 110 degrees in temperature. It only gained 107 degrees in temperature. So we don't care about that 3 degrees other than that's what its starting point was. So I'll put 107 degrees C up here and cancel out that degree C, and then the only unit I have left is my calorie unit. And so I get 0.22 times 75 times 107. So 1766 calories. Looks like I have two significant figures here, so 1800 calories for my answer. Are you okay with that? What's wrong?
Me?
Nope.
How do you decide which one is the one that goes
The smallest number of significant figures. So how many do you have with the 0.22? And the 75? And the 3.0? And the 110? So how many get to use? Two. Well, I told you right off the bat this one was tricky, and I didn't get any questions from anybody over the weekend, so I'm assuming you all got it, right? I hope so. Well, the thing that makes this a little bit tricky is maybe two things. So here's some water, and here's some lead. This stuff is hot. This is cool. I drop this in here, and what happens? Correct. So how did that happen? What was transferred? So Q, right? Calories. Q was transferred. Not degrees C. Transferring with a Q changed the degree C, but that is not what happened. The energy went into the water, and what did the molecules of the water do? And the way you measure that is by measuring its temperature. So you transfer, so then tell me what happened to the lead's atoms. They slowed down. Why did the lead's atoms stop slowing down and the water's molecules stop speeding up? They equalized. So that means that the lead and the water at some given point had an equal kinetic energy. What does that say about if they have equal kinetic energies? Now what do I know? Their temperatures are the same. So the two things that you needed to get out of this, which drawing a diagram might have helped you, was in the end, both of their temperature finals are going to be equal to 22 degrees Celsius. And that the Q of the water is going to be equal to Q of the lead, but the Q of the lead is going to be negative. You got that? What happened to the lead's Q? It went down, so it lost Q. Okay, so if I'm looking for the lead's initial temperature, what I need to know is, because I have the lead's mass, I have the lead's final temperature, I have the lead specific heat if I look it up, and what I need to know is how much energy the lead lost. Okay. Why they're both 22 or why it's 22?
Yeah, why is the final temperature of the lead 22?
Because what was the final temperature of the waters? And where's the lead? So why did the water's temp go from 11 up to 22? Because the lead was hot, right? So the lead was giving it calories and the water temperature was going up. But why all of a sudden did it stop going up at 22? Why didn't it make it to 23 or 28? Or why did it stop at why didn't it stop at 20? So if temperature is a measure of kinetic energy, so that water has a certain amount of kinetic energy at 11, and it's got more kinetic energy at 22. Where did it get that kinetic energy from? The water's kinetic energy is some amount, okay, when it's at 11 degrees Celsius. And then its kinetic energy goes up to 22 degrees Celsius. So it has more kinetic energy now than it did before. Where did it get that energy from? The water got the energy from the lead. So if the water is gaining energy from the lead, what is happening to the lead's energy? It's losing energy. So at some point, the kinetic energy that the water has is going to be exactly equal to the kinetic energy of the what? Of the lead. So that means the lead will stop giving the water energy. And at that point, the water's temperature was 22. So what's the lead's temperature? Yeah. It keeps giving it heat until the the temperatures are equal to each other. Yeah.
I guess I just didn't get that from the question because it says is now at 22 degrees. Like it didn't say it was finally 22 degrees.
But I dropped it in the water.
Yeah. But what if, I don't know, what if it was like, it would continue heating the water, 'cause it doesn't say like it's the final temperature is 22, it just says it's not 22. Maybe later it'll be higher.
What do you think that second sentence should say?
Water started at 11 degrees and, like, yeah, it was finally 22 degrees, finished at 22 degrees, right?
What'd you say?
And then like that.
Okay,
I don't have a problem with the word, I'm just
but my problem with the way you want to word it is, let's say that I waited like, I don't know, 9 hours. Then the energy's going to dissipate to the air. So like, what do I say? Like, I waited 4.5 minutes, or
Stuck around 22 for a little bit.
I stuck around for 22 for a little. I watch it plateau at 22, and then it slowly started petering back to 11. I don't know.
Like the highest temperature it reached was 22?
Until like 6 weeks from now, where it got, 6 weeks ago when it was like 105 degrees in the Dalles, and then everything was over 22. I don't know. I'll think about something, some kind of wording.
Giving us a nicer question.
No, this question has been around for. I had this question, but this question's been around for like 3,000. Let's go with about 1,200 years. Go ahead.
Something that also threw me off is that they added the weight of the lead and the weight of the water, or the grams, I guess.
The mass of the water and the yeah.
Yes, sorry. So if we're doing an equation or a ladder, that's when we use that? The mass? I'm confused. Yeah.
The masses will never be additive. Because they're two different substances. So the mass of water and the mass of lead, since they don't have the same specific heat, they don't behave the same. So you have to do separate calculations. So back to this. I know that the lead's final temp is 22. What I need to know is how much Q it gained, because then I can calculate what its initial temp was if I know how much heat it gained. So what do I need to realize has happened? No. Oh, that's not what I wanted. What just happened? I need to recognize this, which is telling me whatever heat the lead lost was gained by the water. So can I calculate the amount of heat the water gained? Yep, I have enough information to do that. Okay, so how do I do that? Well, I'm looking for a Q at this point, and so I'm expecting, since this was homework, that you guys would look up what the specific heats were. And so I'm going to start a railroad track with 1 calorie per gram degree C, because that's the specific heat of water, and I'm looking for a calorie number, and so there's my calorie number for this water calculation. I need to get rid of the grams by throwing in 175 grams here, and then my grams cancels out. And now I need to get rid of the degree C. What do I put in? 22? The difference between. So in this case, 11. What I care about is how much heat was gained by the water, and the water's temperature changed by 11 degrees Celsius. Okay, so I've got, no, that's not one. Got 175 times 11. Okay, so this is the amount of heat in calories. I don't know why I just wrote degree C. In calories that the water gained. All right? We don't do any significant figure stuff until the absolute final answer. Okay, so this is how much the water gained. So that's also telling me that it's negative 1925 calories for the lead. Okay? Somebody have the lead specific heat? 0.038 calories per gram degree C. And so that's the specific heat of the lead. All right, so what I have here is a degree C, a gram, and a calorie. What I need, since I'm looking for the final temperature, is a degree C. So I'm going to write grams times degree C, 0.038 calories. So I wrote it upside down, which is okay. I can get rid of the gram number by throwing in 75 grams here. I can get rid of the calorie number by putting negative 1925 calories up top, and the calories gone. And then if I take that divided by 0.038 divided by 75, I get negative 600 degrees C. What is that number?
That's the amount of heat that it lost.
Not heat, not calories. No. What does it say? Temperature. That's how much its temperature dropped.
This one step.
Its temperature dropped by 675 degrees Celsius. Okay? So if it ended at what temperature? It stopped falling at 22. Then what temp did it start at? So then the calculation is temperature final, the change in temperature is temperature final minus temperature initial. So what do I have here? Erase. I've got the change in temperature and I've got my initial temperature. So I'm going to take my temperature final is equal to my temperature, my change in temperature plus my temperature initial. Oh wait, I'm not looking for my final temperature. I'm looking for my initial temperature. Sorry, thanks. So temperature initial will be equal to temperature final minus the change in temperature. The final temperature is 22 degrees Celsius. My initial my change in temperature is negative 675 degrees Celsius. And so it'll be 97, 6, 97 degrees C for my initial temperature. I only have 2 sig figs, so we'll go with 700 degrees Celsius. Did you guys get 700?
You got one step short.
Stopped at 675?
Well, we
Yeah.
do put 680.
Yeah.
That's, I did that too. I didn't go through a lot of stuff here, but I got that answer.
Got 700?
I got 680.
Okay. Forgot about that 22. That one was fun, right? Okay, so this one, should you be excited at a sign that says 125? Not so much, because it's a lot slower, right? So it's, you want to know what this is in miles per hour. So it says 125 kilometers per hour. So I need to convert that over to miles per hour. So 1 kilometer, 1,000 meters, and 1 meter, 100 centimeters, and then 2.54 centimeters is 1 mile. No, it's not. Not even close to that. 1 inch, and then 12 inches is a foot, and then 5,280 feet is 1 mile, and the feet, inches, centimeters, meters, and kilometers all cancel out, so I get miles per hour, 125 times 1, 2, equals, I got 77.7 miles per hour. And yes, you need to use this one. Why? It's exact. I don't have to worry about significant figures. You can't use the 1.609 miles per kilometer, kilometers per mile. That's what it is. That one's not exact. Okay, so this one's another thought question. So for something to float, what has to happen? Its density has to be less than 1 gram per centimeter cubed for it to float. Okay, because water's density is 1 gram per centimeter cubed. All right, so if this iPhone and the case together have a mass of 180 grams, what goes down in the denominator that would give me a volume that would allow this thing to float? If I put 181 grams per centimeter cubed, this thing would have like a 0.9-ish. Let's do that. And it would float, right? So any number, any centimeter cube number that's larger than the gram number would allow this thing to float. And any number that is smaller than the, any centimeter cube number smaller than the gram number, this thing is gonna sink. Yeah, I didn't know this, and this happened to me, and there is an iPhone in a waterproof case that's been somewhere in the Columbia for like 5 years now. I'm sure it's still perfectly fine, dead battery, just hanging out, maybe eaten by a sturgeon. Okay, so why is this such a big deal that the Greeks and Dalton have come forth with this atom thing? Maybe you don't think it's a big deal. Wait, say that again? Okay, so this is, this is building blocks, this is structure of matter. Anything else?
We started questioning other than what the church told them, right?
Yeah, sure. Question the church and earlier science. This gave them a biggest part. This was the springboard for all of chemistry and physics. If we were like, this stuff is all atoms, and we can manipulate these atoms, we don't have to worry about destroying them because they can't be destroyed. Let's start experimenting based off of this atom assumption. So lots of things start getting experimented, and many, many things get discovered. Something as simple as, why when I put a glass over the top of a mouse, does the mouse die? 3 minutes, catatonic, 5 minutes, it's dead. Why is that? How could that possibly be? There must be something inside of there that's killing it, right? It wasn't there to start with, but it ends with. So this is something that clergy scientist Joseph Priestley figured out, that oxygen was about. No idea. Nobody knows any of this. They didn't know that there was stuff there. I mean, it's very obvious. A lot of these things to us, once we're told about them, are very obvious, but this stuff was just being made up. No one had any clue as to what was actually going on. So starting off finally with, hey, everything's made out of atoms and we can experiment with these atoms, then people started experimenting. So yeah, basically a springboard. What can you say about the magnitude of the charge of the proton relative to the electron? They're equal. Even though the proton is so much larger, it doesn't matter. They have the exact same charge. So if I've got one proton and one electron on an atom, what's the atom's charge? 0, neutral, it's been neutralized. So what does Dalton say happens during a chemical reaction? Sep R, sep R. R? Which one's wrong? I can't tell. So a chemical reaction occurs, and I got some stuff, and they have formulas. A chemical reaction happens. Those formulas, the atoms get disassembled from each other and then put back together differently. That's it. That's all we've got going on. None of the like 4-element fire, water, earth, and air stuff. None of that stuff's happening. It's much more. You can quantize it and qualify it. Explain why Dalton would be happy to know the chemical formula for water is H2O. What? Okay, so 2 things. 1, whole numbers, and simple ones at that. What else? Always the same. It's always H2O. It's never anything other than H2O. So matter's mostly empty space. Why is that a true statement? What about the nucleus? Okay,
There's
so
big space in between nucleus and nucleus because of all the electrons around, right?
keep going with what you were saying.
The nucleus is on the side.
No, kinda close, but not really. Okay, so the atoms have mass. We okay with that? Most of the mass is where? Most of the mass is in the nucleus. And the nucleus is tiny. Compared to the atom. It's about it's about 10,000 to 1 size ratio. So if I'm looking at an atom, which I can't do, but if I was, there's one speck of mass, and the other 9,999 specks I'm looking at aren't mass. That's actually way more simplified than it is. It's actually smaller than that since we're talking about 3D space. But since all of the mass is in the nucleus, and the nucleus is of relatively volume size much smaller than the rest of the atom, then basically we're looking at a bunch of empty space. Okay. All right. Let's put these 6 people down. So I'll start off with JJ. What was JJ's contribution? Electrons. Positive and negative in atom. Negative can come off. And we'll just say plum pudding. Rutherford? What did Rutherford add? So that the positive of atom is concentrated down into a tiny nucleus. What else we got? What'd Sadi do?
And the neutron? No, the proton.
That Sadi figured out that the nucleus is composed of protons. Not just a solid mass of positive, but individual protons. What about Chadwick? He found the neutron. And what about Bohr? Okay, so planetary model of where the electrons are found. And then Heisenberg. So he determined where the electrons are going to be using quantum mechanics, so basically math.